All right. So, bias and variance are fundamental concepts in machine learning that help us understand how well AI models perform and where they might fall short. So, let's break it down. Bias refers to a model's tendency to consistently miss the mark in a particular direction. In Gen AI, high bias model is too simplistic and makes strong assumptions about the data. It might generate outputs that are overly generic or fail to capture important nuances. So for example, a large generation model that always produces formal business-like language, even when asked to write casual conversation or poetry, right? So that's a bias because it is only knows how to do the formal business language because that's what it's been trained on, right? Or most of the data that is all the data that is seen is all only of formal business written English language. Another example would be an image generation model that consistently produces faces with similar features or ethnic characters, right? Regardless of the prompt. So if you fill it completely with the pictures of me and my relatives, you know, it will of course is going to pick up on the ethnic characteristics and features, right? So variance in Gen AI refers to how much the model's outputs fluctuate or vary for similar inputs, right? So in Gen AI, variance means the model is overly sensitive to small changes in input, right? So high variance means the model is overly sensitive to small changes in input or training data, and it produces wildly different outputs for similar prompts, okay? So a text generation model that produces completely different writing styles or contradictory information when asked the same question multiple times, right? An image generation, high variance might mean generating drastically different images from very similar prompts. So there's a trade-off between bias and variance, okay? So too little bias, complex model, right? The model might fit training data perfectly but fail to generalize well to new situations. Too much bias or simple model, the model might be too rigid and miss important patterns. The goal is to find the sweet spot where the model is complex enough to capture important patterns but simple enough to generalize it, right? So some of the examples, right? Diagnose model problems. Is it too simplistic or too sensitive? Or choose appropriate model architectures and training approaches, right? You can set real expectations for model performance and implement appropriate controls and testing procedures. So to wrap it up, right? Uh, Bias, is defined as the error due to overly simplistic assumptions in learning algorithm. High bias leads to underfitting. Okay, so variance is the error due to excessive sensitivity to small fluctuations in the training set. High variance leads to overfitting. Okay. So bias variance trade-off we talked about, right? A key challenge in ML. So balancing between bias and variance to minimize total error. Why does it matter, you may ask? I mean, reducing bias and variance improves model accuracy and generalization. Okay. So there are, if you're thinking about the evaluation matrix, right? So use matrix like mean square error or MSE, or precision, recall, and F1 score to assess model performance. Right? You can monitor training error and validation error frames, right? So underfitting indicators are high error on training data, modern, model performs poorly on both training and validation sets. So that's underfitting indicators. What are the overfitting indicators? Low error on training data, but high error on validation data. Okay, so underfitting is high error on training data, and model performs poorly on both training and validation data. But overfitting is low error on training data, but high error on validation data. Okay, that's something to remember. So how would you address bias, right? So simplify model architecture, of course, right? Use less complex models like linear regression or logistic regression for problems requiring simpler solutions. And increase training quality, data quality, right? Provide more representative data to help the model learn better patterns. So feature engineering would be add or refine features relevant to the target variable. Regularization techniques would be, introduce penalties to constrain model complexity, and hyperparameter tuning, right? Adjust parameters like learning rate, number of layers on the depth of decision trees to reduce bias. So what are some of the strategies to address variance that we discussed? Increase training data size, of course. The larger data sets help models generalize better, right? And simplify the model. Again, reduce the number of features or prune decisions trees. And apply methods like ridge, lasso regression, or dropout in neural networks to prevent model from fitting noise and data. But don't worry, you're not going to be asked any of this, some of this. And what you may want to remember is what is underfitting, what is overfitting, right? So if a company uses machine learning to predict customer churn using a classification model, right? The initial model underperform on validation data. So what would this step taken, right? You're going to address bias. Add features like customer tenure, past purchase frequency, and increase training data by collecting more representative samples, right? How are you going to address variance? Applied L2 regularization and reduce the depth of decision trees. Use cross-validation to validate performance. So, in conclusion, bias and variance are complementary challenges, okay? Mitigating one often increases the other. So, find the optimal balance. It's an iterative process, so machine learning involves constant evaluation and adjustment of models. And also that the AWS tools that you have available, services like Amazon SageMaker Clarify, can identify and reduce bias. And you can use hyperparameter optimization jobs in SageMaker to tune models effectively. So here's what I want you to do. Experiment with these strategies in AWS free tier using services like Amazon SageMaker.